I want to look at a case where the masses of these cars are not equal. So you can see in this case I've added a big mass, so this car on the left is heavier. And let's continue with a inelastic collision. So they stick together. We still have the Velcro hooked up. And let's see what happens in this case if it's inelastic. So I'm going to have a heavy car crash into a lightweight car. So let's just do that real quick. A heavy car crashing into a lightweight car. We'll have the lightweight car at the stop sign so it's not moving. And you can see what happened. What happened is the cars moved to the left. This is very similar to our other inelastic collision or sticky collision. Two cars beforehand. Let's say that this one is 5 kilograms moving with a velocity of 4 meters per second in that direction. And this one was 2 kilograms with an initial velocity of 0. So what happens? We can say after the collision they were stuck together, and we end up being able to find out 5 kilograms and 2 kilograms. How fast were they moving? So remember, we have the big car colliding with the small car. What do we expect to happen? Well, we obviously expect the big car to slow down and the stopped car to speed up. But by how much? So we can do the calculations. Momentum is mass times velocity plus mass times velocity. Momentum is 5 kilograms times 4 meters per second plus 2 kilograms times 0, which means it is 20 kilogram meters per second. After the collision, the momentum is 5 plus 2 kilograms times some unknown velocity, so it is 7 kilograms times that velocity. Conservation of momentum says that the momentum before equals the momentum after, and we can see that 20 kilogram meters per second is equal to 7 kilograms times the velocity. And if I divide both sides by 7, so 20 divided by 7 ends up being 2.86. I end up with a velocity of 2.86 meters per second. So, interpret. What does that mean? It means that, of course, my big car slowed down and my little car sped up. But by how much? I was going 4 meters per second, and now it's going 2.86, so it lost about 1 meter per second. The little car was going 2, or was going 0, and now it's going almost 3, so it gained about 3 meters per second. So in terms of speed, the big car slowed down a little bit, the little car sped up more, right? Let's imagine a different situation where we really exaggerate this then. Let's look at the case where my two cars, I'm going to say 1,000 kilograms. Okay, here's a car, and here is, I don't know, let's say 100 kilograms. All right, so a person on a bike. Let's do car versus bike. What's going to happen if car hits bike? Let's say that, now obviously nobody was hurt during this experiment, and I'm not going to show you this one, but we'll just do the math and see what happens if a car hits a bike. We kind of know what's going to happen, right? If the car hits the bike and they stick together, because we're going to do an inelastic collision like this, car hits the bike, afterwards, car, 1,000 kilograms, and the bike is stuck on the car with 100 kilograms. Let's see what happens. Let's say that the car is moving some moderate speed of, I don't know, 10 meters per second, 20 miles per hour. 10 meters per second, and the bicycler is just standing there with a velocity of 0, so it's similar to the case that we already did. What's going to be the change of velocity as we do this momentum transfer? Momentum is mass times velocity, 10 meters per second, plus 100 kilograms times 0. So we're going to end up with 10,000 kilogram meters per second. And over here we're going to end up with momentum of 1,100 kilograms times some unknown velocity. Conservation of momentum says that these two are equal, so 10,000 kilogram meters per second is equal to 1,100 kilograms times the velocity. So dividing both sides by 1,100 kilograms, we're going to end up with a final velocity for the car and the bike situation of 10,000 divided by 1,100, and we get 9.1 meters per second. So look what happened. The car was going 10 meters per second. Now it's going 9.1 meters per second. The car didn't change very much. It slowed down a little bit, but not a whole lot. The bicycler was not moving and picked up all 9.1 meters per second, so it sped up a lot. The bicycle had a huge change in velocity. The car had almost no change in velocity. So we can now think about momentum transfer. Did the car gain or lose more momentum? Was the impulse different? Well, you have to think about that. How much momentum did the car lose? And how much momentum did the bicycler gain? Because the bicycler has no momentum now. So we can look at this and we can say, and we can sort of evaluate that in terms of impulse and see which one is actually feeling those effects more. Obviously, to go from 0 to 9, the acceleration is going to be different for the two cars, but we don't necessarily know just from looking at this, without looking at impulse, what the forces are. And we'll look at that on a different problem.